groundwater job. He's really had to come to the We'd like to welcome you all to our Water Talk seminar series today. We have Dr. Quentin Skinner, Professor of Range Management at the University of Wyoming, talk to us today. Quentin has been at the university for at least as long or longer than I have. So that means 20 years or more. And just to give you a little background so that you have a little idea, at one time he was a graduate student in range, microbiology, everything else. So he was actually always in range, but worked in a number of those other areas. He was a ski coach at the University of Wyoming one time. Took him to the national finals a couple of times. Did you ever get first?
No.
Got second, though, didn't you?
Right.
Got second place. And just in the recent past, he joined the range management department in the late 70s, wasn't it?
1978.
1978. And has been with them since. Today, he's going to talk about evaluation of water movement through combusted oil shale using the Environmental Simulation Laboratory. So with that, I'd like to introduce Quentin Skinner.
Well, thank you. I'm going to need the slides. And do the lights come off, or do you leave them on, or how do you do it?
Oh, I got them all. Which one does the...
I'm going to talk today, and I think it's very fitting. I was walking across campus, and I got mowed under by all of the young preps students coming down the walkway hollering, "Save our Earth." And it is Earth Day or Earth Week. I think today is Earth Day. Well, I agree with him. I just don't know quite how to go about doing it. What I'm going to talk today about is the Environmental Simulation Facility and how it can help save our Earth. The Environmental Simulation Facility was built to fit between what we call bench scale research, which is test tube research, and every university and every laboratory of higher learning conducts bench scale research. The other way that we go about trying to save our Earth is to go out in the field and many times use untested products to see if that we can, in fact, clean up field site situations. The trouble with that is it's very difficult to evaluate whether or not what you're doing in field site research actually works. With the Environmental Simulation Facility or concept, we're just about as close as you can actually handle material and ecosystems and still be as close to the real natural field site that you'd want to measure in the first place. Now, the Environmental Simulation Facility is designed to help resolve environmental issues and is designed to take the basic sciences that we develop anywhere in the world, focus those basic sciences at a facility and a way to help answer major program issues or thrusts. It gives us the opportunity to open or close the flow of information, or to constrict or open up the flow of information from the basic sciences to helping save our Earth. I really believe that the Environmental Simulation Facility should be focused on looking at the management of solid waste And that's what we're going to talk about today, is management of solid waste. John Turner from Civil Engineering has got an extensive program that's kind of blossomed out of the work we're doing in the facility on the utilization of solid waste. We for sure in our program that I'll talk about today are looking at transport modeling. We're just about to start focusing on cleanup of groundwater and doing it through bioremediation. Molecular biology is here to stay as a science. It's something that can be evaluated and can be utilized in the cleanup of our earth and of our groundwater, and we plan on using that as a focus in next projects within the type of facility that we have here on the campus. I'll give you a little background about the environmental facility. We built a new ag school, and it was completed in 1981. I was asked at that time what I wanted in the ag school, and I asked them for a watershed lab. First plans for this laboratory were drawn on a napkin in the Union. Since that time, when the building was completed, I had the basics of what we need or needed for the environmental simulation facility. We had a way to store water, circulate water, and circulate it between 0 and a cubic foot per second. The next step that we went through was that the Department of Energy was concerned about solid waste management. I was asked by a congressional delegation if what we have built here on this campus at the present time had ever been reviewed. Tim Reeves, Range Department, developed or helped develop a big portion of the solid waste management program the DOE now has in place. In that process, we did a grant that was in conjunction with the Corps of Engineers of the Waterways Experiment Station in Vicksburg, Mississippi. We toured and worked with scientists from Los Alamos Laboratory. We held a workshop with national and regional scientists as well as other laboratory here on the campus. And out of that grew a competitive grant for looking at solid waste disposal. And out of that we submitted a proposal to finish off the environmental facility that we have today. That facility now is an environmental chamber. It's a prototype. It's the largest environmental chamber that we know of in the world today. It is especially that way because we can take and run the whole hydrologic cycle within it. The guts of the machinery is the climate. We can take and circulate air or a complete air exchange in that 40 times an hour. We can use outside air. We can use just the air within the chamber. We run it through cooling coils, through freezing coils. We get it to a temperature that we want. We adjust the temperature with a heater. We add humidity through steam generation, and we send it back through the system. It'll go from minus 20 degrees Fahrenheit to 120. It'll go from 0 humidity, relative humidity, to 100%. So we've got the climate now within that facility. The next thing that we added was a state-of-the-art in lights that would grow plants. We can have as good a light as any growth chamber going for cool season plants or C3 plants. It'll put 4,800 candlelight at the surface of the pile or the surface of the top of the holding vessels. It'll regulate itself in a diurnal curve, and it gives us about 75% of the intensity of sunlight. Next step that we did in that chamber was to add the Lafayette style rainfall simulator. That simulator system will give you about 70 to 80% of rainfall impact at the surface, and it'll rain from 0 to 5 inches per hour. What looked like a concrete vessel is now 2 holding vessels that we call lysimeters. We split that system in half, making 2. Those are lined with foam insulation, lined with an inert Duracell-like material. And now we have a holding vessel that we can put an ecosystem of soil-like material inside of it. The end of that holding facility or lysimeter has a plexiglass window. Now that window was put in that system so that in biological work we could drill through it and sample at any spot we wanted. Alongside of it, we put in sampling portholes so that we could pipe, drain, sample, wire, do whatever we wanted every foot. The depth of that vessel is, the size of that vessel is 10 feet deep, it's 10 feet wide, and it's 24 feet long. And it holds approximately 220 ton of material. We needed to have a carriage so that we could not only fill the system, but so that we could also sample the system without touching it if need be. So we have a carriage that runs up and down the stainless steel rain gutters. Oh, the last thing that we needed was a system to measure erosion. So we put in a sampling weir that could catch the material as it come off and put it into through a flowing system so that we could collect it. And we have another drain system to collect the excess precipitation. But we also have an inside wall that sits on top of that end so that we can close off if we don't need to access it from the end. So we have, in fact, two environmental chambers, one over the lysimeter and one at the end of the lysimeter. What do we have then? In Wyoming, we have one of a kind environmental simulation facility where we can take an ecosystem anywhere in the United States, we can bring it in, and we can put a climate from anywhere we want on top of it. What are we using it for now? We're looking at how water moves and where it moves through combusted oil shale material. This project is a joint project between civil engineering and ag school. Has 4 principal investigators. John Turner out of civil engineering, Vic Hasfurther out of civil engineering, and Tim Reeves is kind of a toss between because he was a range manager at one time and he does an awful lot of engineering work with Vic and John, so we're going to call him the hydrologist. John really is leading the massive effort within the facility. He's a geotechnical engineer. The essence of this study was to see if water would enter the pile, where it would move, and if in fact it changed the characteristics of this new material. So John has done a pre-sampling, he'll do a post-sampling, and he'll do a sampling after a stressing situation to see if in fact water gets into that pile, if it changes the strength characteristics and what weathering really does to the pile stability so that we can design and dispose of combusted oil shale if it should ever become a nation priority. We haven't forgot the basics. We're for sure conducting the bench scale research. Civil engineering has geared up their geotechnical shop, their hydraulic shops. We're doing a lot of instrumentation work. We have now a climate simulation facility, and we're not building new models, but we're evaluating existing models to look at chemical transport, geotechnical changes in strength, and water movement within large-scale oil shale embankments. Hopefully, at that time, when that material comes out, if it has to be built in the field, we'll have a lot better idea of how to build and dispose of combusted shale in a lot better way. Now, when you look at climate and water input, you have to look at it, or you can look at it in 3 ways. One from a natural evaluation, and that's going out and measuring field sites. The other is we normally model it on existing data sets or data sets that we think would be appropriate. Now with the simulation facility, we can also simulate so that we can gain replication with field and laboratory large-scale scenarios. But most of all, we get the chance to apply the climate extremes over that facility where we can't do that in the field. That means that we can run extreme wet periods, extreme dry periods, and we can keep those modelers honest. We can validate to see what they really say will happen really does happen. Our field site that we put in is in Colorado, Track CA out of Meeker, Colorado. One of the four participants in this study is Rio Blanco Oil Shale Incorporated. Exxon is the other private firm that has given us some help. This is their field site. What they did is measure what we were proposing to do and build us 3 of the lysimeters on their field site. The way we instrumented that field site was that we wanted to measure water 2 ways. We felt very comfortable that neutron attenuation is an acceptable way to measure the flow of water in a pile. The trouble with it is it measures hydrogen, and it measures it in about a foot balloon. So you can't get the detailed movement of water as it goes down through a system. Tim Reeves has spent a good deal of the last 3 or 4 years evaluating a new technique to measure water and modifying it, and that's time-domain reflectometry. So we're measuring water with what we call TDR, time-domain reflectometry, neutron attenuation, and we put in 3 suction cup lysimeters in case we got a saturated condition in the shale pile when water from nature fell on it. We then put the TDR in about every 6 inches, a group of them at the top of the pile, some in the middle, and some at the bottom. At each one of those locations, we also put in thermocouples to measure temperature change within the pile. John Turner put in stress gauges to look at both vertical and horizontal stress as the pile would either lose water or gain water. So what the facility looks at, we've got an instrument shack that collects all the data within and on top of the pile, and we have our MET station up there that has collecting the precipitation, the wind, and the rain, and the solar radiation. And then looking at it from the top, one of the cells is straight combusted shale material. The other one is mixed with straight combusted shale material and overburden. It then has a 2-foot cap of topsoil on top of it. And the third one, the furthest from you, has a surface cap scenario in it, in the fact that it has a layer of straight combusted material and then 10 feet of overburden, or 6 feet of overburden, and a couple feet of topsoil, so that really industry wanted to look at reclaiming their site, and they were certainly justified in doing so. The next step was to build a building out here at the agronomy farm at 7,000 square feet so that we could bring shale in and get ready to put it within our environmental simulation facility. That material was stored and accessed from that facility, loaded using a crane and mixed with the appropriate amount of water agreed on beforehand. That material was then shipped into the campus behind our facility, dumped in a holding bin, loaded onto a conveyor, sent through the laboratory building and into the laboratory itself, and moved on the carriage system and placed wherever we felt it was appropriate to place it at that time. In the meantime, I want to expound just a little bit on the time-domain reflectometry. Tim and the rest of us have got into the habit of mass producing these to put into the facility. So what they look like as they're being built. Really, time-domain reflectometry is no more than a pulse generator that sends electricity or charge down a system. It balances it. It hits where it says the wave guides, balances the beam, and it goes down like radar, and it comes back, and the time it goes down from that transformer to the end and back to that transformer is measured, and that time of travel is modified by the dielectric constant of material. And most minerals have a dielectric constant of about 2, and the water has it of 8, so we can tell how much water is in that material. For sure, time domain reflectometry is something could be another seminar subject for this water effort. And this is what they look like as we're laying them in. The advantage of this is we can measure water every ½ inch to 2 inches or further apart as it moves down through the profile. That way we can give the hydrologist and the other people an accurate look at the movement and redistribution of water in the pile. This is a typical stress gauge that John put into the piles. This one's going to measure vertical pressure, and if it was on edge it would measure horizontal pressure. Material was then spread. We brought it up in 12-inch lifts. We compacted it to a predetermined density, both down in the field side and here. You can see that the instruments, as we're going up, are tied to what we have as 3 instrument trees. After we compacted, we took and did the gamma radiation, determined the dry and the wet densities. We also, each load, took the soil samples or material samples so we could determine soil water by gravimetric pressure techniques. So as we built the pile, we were very, very sure of what the characteristics of the material was when we placed it, so that we could come back later and see how that had changed as we destroyed the pile. The reason we have such a large facility, or one of the reasons, is to get away from boundary effects that occur in bench scale and column type engineering studies. We want free boundary conditions. Therefore, the majority of our instrumentation sets 3 feet from each sidewall and 5 feet from each end. We do have, you can see a couple TDR probes running out near the edge, and that's to see if we get any sidewall effect during the term of this study. The last thing we did was put in our weather monitoring facilities within the chamber itself, so that we could compare how this thing is working compared to what we ask it to do from Mother Nature in Colorado. Gives you an idea of the distribution of the instrumentation that we have in there. I think there's 72 time domain reflectometry probes spread every 2 inches near the surface, a gap in the middle and some in the middle, and then again some in the bottom. And then we have a few scattered over on the sidewall to see if water is really coming down through it. What have we got then? What we're doing is taking Mother Nature at the field site. We're monitoring Mother Nature. We're bringing it in. We're storing it in a database. That database is then modeled and sent to a driving program that we've got on a computer attached to the facility. That computer driving program tells the climate control system, the DSC 8500, what temperature and what relative humidity we want to see in the chamber. Now, if we want a rainstorm, that's plugged into the driving program. It tells our rainfall controller how to rain on that system. And depending on what we measure in light down on the field sites, it tells us what we want as far as our light source. Well, how's it work? We have 2 general storm patterns in Wyoming, one for storms over 4 hours and one for less than 4 hours. And we covered, when we built the piles in Colorado, we covered that pile and we didn't uncover it until the middle of December. Now, we did that for a reason. The reason was is we wanted the pile to be frozen, and we wanted the snow to pack on it, and we could then get an accurate measurement of the water that was coming off snow melt into it while we built the environmental simulation facility. So what we're doing, we're going to apply that snow melt on that pile in the general storm pattern of over 4 hours. And this is what the rainstorm actually looked like. We'd put it on there over 48 hours. So it fit very, very well. We did not lose any of the water as runoff. Neither did we in the field. The next type of pattern is one that's less than 4 hours, or our typical convective storm model condition. And a typical rainstorm under 4 hours that we've applied comes out very well. So we feel we can model the storm under our general pattern and apply them to the pile, and they come out fitting the modeled curves pretty well. Well, let's see some data that tells us that. This chart shows that we've measured using time domain reflectometry and neutron access, the neutron attenuation. We've measured the typical soil water that's in that pile from October 20th to after what we felt snow melt had occurred. And so that figured out to be about 1.9 inches of water. Well, then we went in and in September, we put the 48-hour storm on in September, and 9 or 8 days later, we measured it, and lo and behold, we have the same general kind of curve. Well, how did it turn out? Let's compare it to the other two. The general storm that we applied. Well, after we applied 1.9 inches to that pile, we measured in our own lysimeter 1.6 inches. Now the difference lies in the fact that we have closer instrumentation. We have closer instrumentation to the surface in our lysimeter in Laramie. This is the lysimeter and this is the field site. We have them instruments every 2 inches here, so we knew where this line come back. Here, we didn't know where it is. That line could have come back somewhat like that. So we over-measured what was in the field. The other thing that we haven't got is we measured 1.9 inches in the field, put 1.9 inches over it, got 1.6 inches. This would make it even closer, and then the rest would be evaporation from the top of that pile. So really you're looking at evaporation off of the lysimeters here in Laramie of being about anywhere from 2/10 to 3/10 of an inch in water. So that's very, very accurate. Now what have we measured after we rain? I better get my pointer here. We model the climate we get off of the field side, and we're going to call that the set temperature and the set relative humidity. And then we measure what actually occurs in the chamber. This is right after we put snow melt, or the 1.9 inches on the pile. We also had a number of rain events. That means that our relative humidity during this wet period is about 30% higher than the modeled condition. As this pile goes, it dries out, and we've only got about a 15% difference here. What is happening? It's evaporating the water out of the top 2 inches of that pile. Therefore, the set and the modeled condition, or the actual and the modeled conditions, have a difference. Now as it's drying out, and I put this slide in to show you that you can measure diurnal change in relative humidity. As temperature goes down, relative humidity goes up. It also gives you the ability to measure the change in relative humidity during a rainstorm. As we're drying out, we're getting closer and closer between the modeled relative humidity and the actual. Very important to note that modeled and actual temperature run hand in hand. In periods of when rainstorms aren't there, our relative humidity and our modeled and our actual come right together, and it's only diurnal change. I don't have a slide showing the extreme dry periods, but they run together, both temperature and relative humidity. In summary, we sit down and think about it, we have a unique facility. We have an opportunity to do a lot for what the kids were hollering today, save our earth. It's one of a kind. I feel that the project team and the machine is going to advance the state of the art on solid waste disposal. With that, I'd be glad to answer any questions. Yeah.
How long does it take to set up and run one of these tests? We're looking at 6 months, 2 years, 4 years?
Well, we're looking at another 2 years just to look at stressing that pile. We've gone through a lot of mistakes, a lot of trials. We're proving to see, or trying to see, if in fact we can replicate field conditions with the facility. That took us a good length of time on this project. We're also scheduled to look at how eastern conditions, or bring eastern shale in and use the eastern climate and see if we can replicate eastern climate field conditions. Now, if we can do both west and east, that means that we don't have to go to the field and build the lysimeters and take it. We can take climate data sets or just data from the field site and replicate those data sets on the ecosystem that we wish to put in that facility here in Laramie. That time then will shorten. I think that if you're going to stress the climate thing, I think you're talking about 2 years in that facility at a minimum, wouldn't you, Vic? I wouldn't want to put that. It takes 6 weeks to build that system or load that system, and I should have used 12 weeks because you're no better than what you know you put in. And so when you put something in there, you have to do a lot of science and monitoring of the materials that go in there. And then you should really measure what comes out. So I guess you're looking at a 2-year project every time you move something in there. But you're working with a material here. If you're working with an oil spill or you're working with cleanup of groundwater, there's scenarios that we can cut that time down immensely. Yes?
Quentin, do you do anything with wind speed in the chamber?
We do not do anything in wind speed. We could measure what blows through there, that's for sure. The reason we didn't is because when we went through the engineering design of this, to make wind takes a lot of facility space, and we did not feel that wind was that important. And maybe we're going to show that wind isn't that important once you evaporate the first 2 inches of water in that system. Now, you have to give and take at places, and wind speed and wind, when they described what it took to make a wind tunnel, we decided that was something we could do without. So it's not a panacea for everything, but we're really interested in looking at the transport system of water. And
Could you explain explain a little bit about how the time domain reflectometry measurements are affected by the degree of soil moisture saturation?
Yes,
So there are a couple of different filters,
well, as
like
soil water increases and finally gets saturated, time domain reflectometry doesn't work. It works up to saturation. And the more water you got in the system, the more time it takes to travel through it. And because minerals is a dielectric constant of 2, water's a dielectric constant of 80. As you add water, you slow, am I right? You slow it down. So it takes longer. So, and then the formulas and the magic of mathematics calculated out that they're actually very close to water content, tested through gravimetric procedures. All I know is it'll handle high salinity. It will take a real beating with vibrating machines, and I can measure water accurately as it moves in a profile. And I think it's the state of the art in measuring soil water. And Tim has built the only probes that I know of that you bury and can bury and leave in the ground. They have time domain or TDR units to go poke into the soil, but the meters and everything are on the surface. So it's to his credit that he took it on himself and really got us into business.
There was a variation between the, I believe it was the relative humidity that was modeled and what you'd seen as actual. Are you taking any steps to bring that closer together, or what is the explanation that you see for that difference?
You will not bring those closer together until you dry out the top 2 inches after water's been put on that pile. It has to dry out just like Mother Nature. I'm sure that's over the top of it too. When it is wet, it dries out the surface, whether it's the first 2 inches, I don't know, but 2 inches, your evaporation loss becomes very little out of a pile. But as you dry out the surface of that pile, first of all, it won't even change. The modeled condition and the actual will be right together during a small rainstorm. Doesn't even change it. It's when you soak that water into the pile and it comes back out of that it does change. And so during dry periods, they run right hand in hand. So I feel it's just a case of drying out that surface. Now, if in fact the field water content of those lysimeters are the same as what we've put on top of them here in Laramie, then I'm not going to worry about the difference between the relative humidity, because the evaporation loss occurred there as well as here. The proof of the pudding is how close is the water content down there with the water content up here, based on the rainstorm and the precipitation records that we place over both.
What was the purpose for wetting down the soil mixture before it was put in the container? Because it doesn't sound like something that would be done out in the field with oil shale material.
Oh yeah, it will. I'm going to make sure they do. First of all, they have a degree of water that they have to put on for dust control. Now the water that we put on the shale, both down there and here, was what they calculated they needed for dust control, not for stability. John Turner told them they need to put about 28% water for optimum engineering characteristics, and they said we'll be lucky if we'll put 10%. And we went 15% because 5% is tied up in the hydration of the new materials. So you're talking only 10% water. But now they will tell you they don't want to put any water on you, but I don't think the permitting and environmental constraints are going to let them do something like that without dust control. And they agreed. So the amount of water that was put on there area was for dust control only. The size of the particles I don't know for sure, but it's about like cement that you throw in sand. So you're definitely going to have dust. Yes.
Does the project call for looking at an addition of soil moisture content and the physical characteristics of the pile, under the environmental scenario that exists at Rio Blanco? How long will it take for the pile to reach some level of moisture saturation, and do you expect to see any leachates out of the pile, and will the characteristics of those be measured?
Industry will maintain that water would never get through that pile. We don't know that because Dave Gutberg here is developing soil water curves and everything else, and then the models will predict. It's not so much how much water will get through the pile, but it's what's happened if you get sidewall migration from valley flow or anything else into it. And these piles are designed or have been proposed to be the largest structures man has ever made. And it's what water is there during the winter or whatever that's collected, put under a lot of pressure that may cause failure that's a concern. But I'm really convinced from what we're learning that the engineering profession will be a lot closer to designing an excellent scenario for disposal of combusted shale materials than they were before we started this work. So that's a step, and telling you how long it'll take won't come until we test the available models to see how long it'll take. We're just not there.
At this point, we haven't seen any moisture moving deeper than 2 feet approximately, is that right, into the pile. And that's with any type of rainstorm that we've seen so far, where we're just modeling the climate. So in this dry climate, looks like, it's tough to do, and we're just getting to the point where we're starting to model some of that type of stuff to see whether we think it's going to go down there. But we still need the permeability characteristics and the hydraulic conductivity characteristics that we're developing in the laboratory even to get a better prediction of whether we think that's going to happen or not.
And we look to be done with that effort by March, and then look at stressing the pile from then for another 1.5 years or 2, and then go from there, hopefully, to new and different things. How about that? I appreciate very much the opportunity to talk to the group about it.
We'd like to thank Quentin. I'm sure if you have any other questions, he'd be happy to answer them if you stick around. Next week, I didn't bring my list, but I believe it's, we're going to look at a chemist stuff to try to monitor